Hello everyone, this is Sir Aris. Today we will talk about the last part of our discussion on complex numbers. Specifically, we'll talk about logarithm, um, complex roots and powers, inverse trigonometric, and hyperbolic functions. If you have a complex number z equal to e to the power of w, then by definition, w equals ln of z. Ln here is our definition, is our symbol for natural logarithm. So that if we get ln of x, that's equal to log to the base e of x. Using the law of exponents, it can be shown that this will apply to complex numbers also. So z1 equals e to the power of w1, z2 equals e to the power of w2. Um, z1 times z2 is equal to e w1 times e w2 equals e w1 plus w2. If you take the logarithm of this equation, you have ln z1 z2, or ln of e to the power of w1 plus w2. So this, let me write it here, is equal to w1 plus w2. This is an identity, ln of e. So e to the power of w1 plus w2, we bring that down, times ln of e. ln of e is 1, so that you have w1 plus w2 is equal to ln z1 plus ln z2. So the real and imaginary parts of the logarithm of a complex number can be found using this equation, where z we write as magnitude r times e to the power of I theta. And we can separate these two just like what we did here. You get ln of r plus ln of e to the I theta. But take note here, I have used capital letter L. So capital letter L and R plus this I theta, we can bring it down so that L and E is just 1. So you have I theta. Capital letter L N means that you have an ordinary real logarithm to the base E of a real positive number R. So if you have this, it's understood that R is a positive number, or you can think of it as, say you have Ln of X, that's equal to Ln of absolute value of X. Typically, if you are not talking about complex numbers, you can just write uh, L, small letter, capital letter. There is no difference. But here, since we are talking on complex numbers, we have to uh, give this a separate uh, definition, L and X. The angle theta has an infinite number of values, each differing by multiples of theta. So the reason here is because if you have complex plane xy, you have this angle theta. If you go around, rotate 360 degrees, that's still theta. So theta plus, let's say, 2 n pi will always be that angle. So that's why it's theta differing by multiples of 2 pi. The principal value of L and Z is the one using the principal value of theta. That is theta between 0 and 2 pi. 0 and 2 pi are the same, so we choose 0. We only use 0. If we encounter 2 pi, we just set it equal to 0. Example, find ln of negative 1. You might have known that ln of negative 1 does not exist, but the reason is that um, without thinking about complex numbers, there is really no natural logarithm of negative 1. But if we think of negative 1 as a complex number, so negative 1, if z equals negative 1, um, in the complex plane, that is over here, so that's the real part is minus 1. So it's equivalent to uh, a complex number with, so this is minus 1, with magnitude 1. So this one is 1, but with an angle of pi. Okay, so z equals 1 e to the power of uh, theta, let's say I theta, where theta equals, um, let me write it completely. Okay, theta or r is 1, theta is pi, it could be minus pi, it could be 3 pi, and so on. Essentially, you can write theta as pi plus minus 2n pi. So that here, ln of negative 1 would be ln of um, r ei theta. So r ei theta, or ln of r plus ln of ei theta, which is just ln of r plus I theta, ln of e, which is 1. Okay, our definition, that's our equation here. Okay, so ln of r, we have r is 1, okay, plus I theta is pi plus and minus 2n pi. So these are all the values of our ln negative 1. So ln negative 1 equals um, I pi, it could be minus I pi, it could be 3 pi I, and so on. So these are all the values of our ln of negative 1. Another example, find ln of 1 plus I. So here, 1 plus I in the xy complex plane. Say this is 1, minus 1, 1, minus 1. This here is our 1 plus I. Okay, or let's say this line here. Let me leave it like that. Or the magnitude is here 1 squared plus 1 squared, that's square root of 2, that's 2, take the square root, so the magnitude is square root of 2. The angle here, we know that this is pi over 4, but you can add by 2n pi or subtract it by 2n pi. That would just be the same, plus minus 2n pi. So 1 plus I can be written as square root of 2 e to the power of I pi over 4 plus minus 2n pi. Okay, so ln of 1 plus I is simply capital letter ln of square root of 2 plus I of pi over 4 plus minus 2n pi. Okay, and that would be the simplest form. Now let's consider complex recent powers. Suppose you have two complex numbers a and b. If you take ln of a to the power of b, b simply goes down here outside of ln, b ln a. So if you exponentiate both sides, so e ln of a b becomes a to the power of b, and then e to the power of b ln a, so that's this one. Okay, we can make use of this to solve for this kind of expression. Find the values of I to minus 2I. Um, so here we will be needing, so I to the power of minus 2I is equal to e to the power of, so here if you write it as a to the power of b, then you have a equals I and b equals minus 2I. So you have e minus 2I ln of I. And we need the value of ln of I. How do we get that? So if you look at the complex plane xy, 1, 1, minus 1, minus 1. So this is our point I, okay, with magnitude 1. So I can be written as 1 e to the power of I theta. Theta here is pi over 2 plus and minus 2n pi. So add 360 degrees or subtract 360 degrees, that's just the same. So e to the power of I pi over 2 plus minus 2n pi. Okay, so ln of I is equal to ln, capital letter ln of the magnitude, which is 1, plus I theta is pi over 2 plus and minus 2n pi. Okay, so we simplify. So we write I to the minus 2I, that's equal to e to the minus 2I of ln of I, which is this. Ln of 1 is 0. Okay, so we have I pi over 2 plus and minus 2n pi. So that's 2. I times I is minus 1, so times minus here is just 2. 2, we can distribute that here, pi over 2 and 2n pi. So you have um, pi e to the power of pi plus and minus 4 n pi. Or simply you can write I to the power of minus 2I. That's equal to, by the way, I normally write I like this, but you can write it in any way you like. Say I like that. The minus 2I equals e to the power of pi plus minus 4 pi. So that could be e to the power of, say if n is 0, so that's pi. If n is 1, that could be e to the minus e to the 5 pi, or e to the minus 3 pi, and so on. Okay, another example. Find the values of I to the power of 1 half. Here, um, again, if you have I to the power of 1 half, that's equal to e to the 1 half and ln of I. And I think we have already solved ln of I. Ln of I over, where was that? Ln of I is I pi over 2 plus minus 2, 2n pi. Okay, so this is, oops, e to the power of 1 half. Ln of I is I pi over 2 plus and minus 2n pi. Let me check if that is correct. I pi over 2 plus minus l 2n pi. Okay, so if we distribute, you have e to the I pi over 4 plus and minus um, n pi. Okay, or this can be simply written as e to the power of I pi over 4 times e to the power of I plus minus n pi. Okay, so e to the power of I n pi have only two values. It would be plus 1. So if n is even, and it would be minus 1 if n is odd. Okay, if you look at complex plane to verify, ei and pi means you have four even multiples. So the magnitude is always 1. It could be either this one or this one. If it's this one, it means that n is uh, 0, or the angle is 360 degrees. So that's why if n is multiple of 2 pi, n is even, um, we get plus 1. If n is odd, or if n is, say, pi, or minus pi, or 3 pi, 5 pi, minus 3 pi, minus 5 pi, and so on, we get negative 1. So there are only two values. So regardless of this being plus and minus here, we only have two values for this term here. It is either multiply this by plus I, or plus 1, or minus 1. So I to the power of 1/2 is equal to plus and minus e I pi over 4. Okay, or actually we can further write that into um, I 1/2 equals, so I pi over 4 in the complex plane. So pi over 4 is this. Okay. Um, this is, if this is 1, then this uh, x position, or x distance here, is, that's pi over 4 cosine of pi over 4, that's square root of 2 over 2. Here, this is square root of 2 over 2. So these are the x and y components. So here we can write as plus and minus square root of 2 over 2 plus I square root of 2 over 2, or plus and minus square root of 2 over 2, 1 plus I. Okay, another example. Find the values of 1 plus I to the power of 1 minus I. So from our expression equation, 1 plus I, or actually just to write it smoothly, we need ln of, so actually we know that ln of 1 plus I, so let's return to our previous equation, example. Ln of 1 plus I is ln square root of 2 plus I pi over 4 plus minus 2 n pi. We'll use that. um, ln of 1 plus I is ln square root of 2 plus I pi over 4 plus minus 2n pi. Okay, so that 1 plus I to the power of 1 minus I, which is e to the power of 1 minus I, times ln of 1 plus I. Okay, this is equal to e 1 minus I times ln square root of 2 plus I pi over 4 plus minus 2n pi. And then next step, I will write it. I will continue the equation here. So we just multiply minus I times this. So you have e to the power of ln square root of 2, e to the power of minus I ln square root of 2, e to the power of this I pi over 4 plus and minus 2n pi. Okay, or let me separate that. I pi over 4 and e to the power of um, plus and minus 2n pi. Okay, and then here I times this. You have e the power of pi over 4, and there's an I here that I forgot. Okay, e to the power of plus and minus 2n pi. Okay, what is e to the power of I 2n pi? Regardless if this is plus or minus, this will always be 1. Okay, again, complex plane. Here, 2n pi means you go 2 pi multiples of that 2i multiple. So that will always go back to this 0 degree. Okay. Um, what else? So we have ln square root of 2, e to the power of ln square root of 2, that's square root of 2. So we write first terms that have no i's in the exponent. You have e pi over 4 and e plus and minus 2n pi. So that's this two, this and this. And then e the power of I pi over 4, this one pi over 4 minus ln square root of 2. Okay, or square root of 2 e pi over 4 e plus minus 2n pi cosine of pi over 4 minus ln square root of 2. Okay, we're evaluating this. Plus I sine of pi over 4 minus ln square root of 2. So that's our 1 plus I to the power of 1 minus I. Okay, so last section, inverse trigonometric and hyperbolic functions. So we'll have right away an example. Find z where cosine z equals 2. So it means that z, in this case, z is simply arc cosine of 2. Okay, but we don't know, or we don't have an expression yet for uh, arc cosine of 2. So it'd be best to start with cosine z. Okay, cosine z equals 2. Cosine z, we have known this as, so cosine z equals eiz plus e minus iz over 2. So that's equal to 2. So what we can do, we substitute uh, for a variable on, we substitute this eiz with a variable u. So you have u plus u minus 1 divided by 2 equals 2. If you multiply by 2 on both sides and multiply it by 2u on both sides, so you have u squared plus u equals 4. No, not u. If you multiply 2u here, u cancels, 2 cancels, so that's 1 equals um, 4u. Or this becomes u squared minus 4u plus 1 equals 0. So using quadratic formula, this is 4 plus minus square root of 4 squared minus 4ac. So that's 4 divided by 2. Okay, so we can simply simplify 4 plus minus square root of 16 minus 4, that's 12 over 2. This is 4 times 3. Square root of 4 is 2. So divide by 2. You have 2 plus minus square root of 3. Okay. But u is equal to um, e to the iz. So this one equals e to the iz. So we take ln of both sides. This and this. So you have iz equals ln of 2 plus minus square root of 3. Okay. Now ln of 2 plus minus square root of 3, that would be equal to capital ln 2 plus minus square root of 3. Um, treating this as a complex number, so with theta equals multiple of 2 pi. So you have here I 2n pi. Okay. Now multiplying both sides by minus I, you have z equals minus I ln 2 plus minus square root of 3 minus I, so that's plus 2n uh, 2n pi. Okay, or if you want to rearrange, that would simply be z equals 2n pi, um, or there's something that we want to add. We use ln, so using the um, identity 2 minus square root of 3 equals negative ln 2 plus square root of 3. That would be easy. Ln 2 minus square root of 3 means you have ln of 2 times ln of minus square root of 3. You can take out, uh, you can turn minus square root of 3. So then eventually you can write negative ln of 2 plus square root of 3. So that ln of, so we have ln of 2 minus or plus and minus square root of 3, that's equal to plus and minus ln 2 plus square root of 3. Okay, so finally we can write z equals 2n pi plus and minus I ln of 2 plus square root of 3. And last example, evaluate z, which is equal to hyperbolic sine inverse of x over a. So we can write x over a equals hyperbolic sine of z. Hyperbolic sine of z, by definition, that's easy minus e minus z over 2. So if we let u equals easy, then we have x over a equals u minus u inverse times 2. So you have here u inverse u to the minus 1. Multiplying both sides by, say, 2u and a. So you have, multiply here 2u and a. Here you also multiply 2u and a. So you have here 2ux, 2 and 2 cancels. So you have u squared a minus a. u minus 1, u a. So you have a u squared minus 2ux, or 2xu, x being just a some number, minus a equals 0. Okay, so we're looking for u. U is or negative 2x plus minus square root of 2x squared minus 4ac all over 2a. Okay, so the 2's actually cancel. There's 2 here, there's 2 squared here, and there's 4. They cancel out. So you have x plus minus square root of x squared minus or plus a squared over a. And this is equal to easy right here. Okay, so if we take the logarithm on both sides, you have ln of e to the power of z equals ln of x plus minus x squared plus a squared over a. So here you have z equals ln of x plus and minus x squared plus a squared minus ln of a. Okay,